what does number 16 say?
Propose two-step mechanism.
Okay, propose a two-step mechanism for the ozone decomposition. So step 2 is the RDS. We didn't look at this. Did we talk about ozone? Unimolecular? Did you get a question about that? No? All right, so the reaction is 2 ozone goes to 3 O2s. And we might have a bimolecular collision. If we have a bimolecular collision, then we have an ozone plus an ozone yields, what would happen? An ozone plus an ozone would yield 3 O2s. If we had a bimolecular, then this would be a single step reaction. But they're asking for a two-step reaction. And so, since this is a single step, that's not what they're after in this particular question. And so we need a two-step process. So we have to go to unimolecular because that's the only other option, because we could have 2 ozones collide or 1 ozone. We don't have 3 ozones, we can't go trimolecular. And so if we have a unimolecular, we have to figure out, if it collides with the wall, what could it decompose into? It's possible.
O2 and O.
It could decompose into O2 and O, or a whole variety of them. Did we talk about this already? It's a multiple choice question. Yeah? Okay. So we'll call this step 1. Step 1 is going to be fast and reversible, let's say. Then we go on to step 2. Step 2, but O is what we call an intermediate, so we got to get rid of the O. One way of getting rid of the O is we have one more ozone that needs to react. So if an O reacts with an ozone, what can we form? Here. If an O reacts with an ozone, what could we form? 2 O2s, right. 2 O2s. And so if we add up these, then the O cancels out, that's an intermediate, so we'll get ozone plus ozone. This is going to yield 3 O2s, basically. And so we get 2 ozones goes to 3 O2s, which checks out. So the net reaction is the desired reaction. So that's it. And so we're calling the second step the slow step. So we'll label these. This is going to be K1 forward, K-1 reverse, K2 forward here. And so the rate of the slow step is the rate of the overall reaction. The rate of the slow step is going to be K2 here times the O concentration times the ozone concentration. And then we do the fast reversible. Well, we could use the fast reversible, but in this case, we're not going to use the fast reversible. We're going to use the steady state approximation. Steady state approximation says that the rate of O formation is equal to the rate of O consumption. So the rate, how is O being formed? It's being formed by K1. K1's forming it. And so if K1's forming it, then the rate is going to be K1 times the O zone. How is it being consumed? It's being consumed in 2 ways. O is being consumed by the reverse reaction here, K-1. And so that would be K-1 times the O2 concentration times the O. And it's being consumed by the forward reaction here, K2. So this is going to be plus K2. this shouldn't be negative, it should be plus K2 times the O times the ozone. And so what we'll do is we're going to factor out the O and solve this. So for O. So O is going to equal K1 times the ozone here, divided by, okay, if we factor that out, we get K minus 1 times the O2 here, and plus K2 times the O3 here. Then we substitute that back into this equation here. So we get the rate is equal to K2, now substituting this whole thing, with K1 times the ozone over K minus 1 times the O2 plus K2 times the ozone here, times the ozone concentration. And so, we'll just multiply that throughout here. So we'll call K2 times K1 K prime. So this is going to be ozone squared over K minus 1 O2 plus K2 O3.
Why did you put plus K?
This one?
Yeah.
Why? Because how are we losing the intermediate O? Where's O being lost? O is being lost going backwards here, and O is being lost going forward here. And so O is being lost in two ways, so that's why we have to add them up both ways. It's being lost. So it just asks to solve using steady state approximation, that's it?
Yeah, divide the rate law.
All right, then that's it, we just derived the rate. Okay, so that's how you solve that particular problem. Other questions? No? We're going to go to chapter, back to chapter 19. Where did we leave off in chapter 19? What were we talking about? Did we calculate the temperature already at which the reaction went from non-spontaneous to spontaneous? Did we calculate the temperature for that? All right.
didn't. Okay. Did we actually calculate a temperature value or not?
Yes, we did.
Oh, we did? Okay.
Okay, we're going to look at this. We have delta G standard. You know, we had it at 298 Kelvin, or we had it at temperature T. And so under standard conditions, we have two options. We could do it at 298 or we could do it at some other temperature. And so the equations that we deal with are delta G naught at 298 Kelvin is going to equal delta H naught minus T delta S naught. This has to be at 290 Kelvin, this has to be at 298 Kelvin, and the temperature has to be at 298 Kelvin. So we can figure out what our driving force is at 298 Kelvin. If we're at 298 Kelvin, we have another option. You know, the other option is actually even easier because we can calculate delta G naught using the sum of the delta G's of formation. And so the other thing is from Appendix D, the second column is what we call standard free energies of formation. These are standard enthalpies of formation. With the standard free energies of formation, we could just look at the coefficient, that is the moles of product, times the delta G of formation under standard conditions of the product, minus the sum of the moles of reactant times the delta G of formation under standard conditions for the reactant. And so this is even easier. It's just like calculating delta H. You know, you just take the free energies of formation for the products minus the free energies of formation for the reactants. We're done. At temperatures that are not at 298 Kelvin, let's say, just some standard temperature T, then we need to know the data. So for example, if we're looking at delta G under standard conditions but at a different temperature, then we need to know delta H under standard conditions at the temperature minus T delta F under standard conditions at the temperature. The problem is we don't have the data for delta H and delta S. And so what we'll do is we make the assumption that delta H and delta S don't change that much with the temperature. And so we say that delta H at 298 Kelvin is about the same as delta H at some other temperature. And delta S at 298 Kelvin is about the same. And so as long as the phase doesn't change, this is okay. Okay as long as the same phase. That is, it stays a solid, it stays a liquid, or it stays a gas. Now, can we say this? Can we say that that delta G naught at temperature T is equal to the sum of nu, the products, times the delta G's of formation of the product, minus the sum and dot, dot, dot. Will this work? Yeah, this will work, except we need to know the delta G's of formation at temperature T. Do we have the delta G's of formation at temperature T? We don't. We have the delta G's of formation at temperature 290 Kelvin, which is in Appendix D. Well, can we say that the delta G's of formation, you know, this is at temperature T. Can we say that this is about the same as delta G of formation at 298? Is it possible to just go ahead and use the delta G's of formation at 298 for this? No. Because the delta G changes too much with temperature. And so we can't do that. And so we don't have the data, so we aren't going to use that equation. And so this only works at 290 Kelvin, then we're okay. But at any other temperature, it's not. And so for a delta G, at some other temperature, we have to use this equation here. And so it's important that we keep track of the temperature, otherwise we might end up with the wrong equation. A lot of people
A lot of people have a hard enough time just keeping track of units, you know? But that makes thermodynamics especially tough because you got to keep track of all these things, and you know.
Professor, is that frequency?
No, that's the symbol for moles, the coefficient, you know. So if you have 2 moles of product, then we have to do 2 times the delta G of formation of the product, because the delta G of formation of the product is per mole. All these are per 1 mole. It looks like frequency. Nu is frequency, but Petrucci uses that symbol for this too. So we did a calculation at an alternate temperature. We did this calculation by just plugging in temperature here and using these values of 298. But the other thing is, we might not do every reaction at 298 Kelvin. And the same goes for this. We might not do every reaction at 1 molar concentration. Do you use 1 molar for everything? No. And so if you don't use 1 molar, then we aren't under standard conditions. Standard conditions is just kind of strange because standard conditions, you know, when we think about standard conditions, you know, all the concentrations are equal to 1.0 molar. Let's see, 1.00 molar. All the concentrations are 1 molar. They will exactly 1 molar. That includes the reactants and products. Reactants and products are 1 molar, and all the pressures are at 1 bar or 1 atmosphere. So under standard conditions, our Q is kind of interesting because under standard conditions, our Q looks like this. Our Q is just the activity of the products over the activity of the reactants raised to their respective powers. Right? And if all the gases and all the solutions are 1 molar, 1 atmosphere, 1 bar, then Q is always going to equal 1. That's the reaction quotient, the thermodynamic reaction quotient. So this gives us an interesting thing to think about. Under standard conditions, if delta G naught is greater than 0, then what this means is in terms of equilibria, a delta G naught greater than 0 means it's unfavorable, right? The reverse reaction is spontaneous. So that means that Q is going to be greater than 0 because we got too much product. This reaction should shift left. Putting the Le Chateliers or whatever. If delta G naught is equal to 0, that means we're at equilibrium. So if that delta G naught is equal to 0, Q is greater than K, then Q is equal to K. Well, this is odd because, you know, a delta G naught equal to 0 means that the equilibrium constant K must be 1. How many equilibrium constants do you know that equal 1? None, probably. But the thing is, K, like delta G, depends on the temperature. So if you change the temperature, you can change K. And so in that last problem, what we're doing is we're figuring out a temperature in which the K is equal to 1. Therefore, under standard conditions, we're at equilibrium. If delta G naught is less than 0, then Q is less than K, and we expect forward reaction to occur. We have driving force. Now, What if we go non-standard conditions? We could have non-standard conditions come up in two scenarios. One, we could be at 298 Kelvin. And the other, we could be not at 298 Kelvin. So under non-standard conditions, what we do is we take, this is delta G under non-standard conditions at 298 Kelvin. This is going to equal delta G under standard conditions at 298 Kelvin. So we just take our delta G under standard conditions and then modify that for non-standard conditions by adding this factor, RT ln a cube. The derivation for this is in the book. I'm going to skip it entirely, but this is what we do for non-standard conditions, is we add this factor here to our standard here. Okay, again, this is Q. Q would be the thermodynamic equilibrium reaction coefficient here. T, well, we already know the temperature is going to be 298 Kelvin here. So what we can do is we can alter concentration or pressures and or pressures to change the driving force. Okay, what if we do both? What if we change to non-standard conditions and we change the temperature so the temperature is not at 298? And so if we're just looking at any old temperature under non-standard conditions, we have delta G under that temperature, which is going to equal delta G naught at that temperature plus RT ln of Q. So in this case here, is it possible to say that this is going to be approximately equal to delta G naught at 298 Kelvin? No, that's not possible. We can't do that. What we have to do is we have to calculate it. Delta G naught under standard conditions at some other temperature is going to equal what? Well, this is going to equal delta H naught at that temperature. Yeah, minus T delta S naught at that temperature. Do we know what delta H and delta S are at different temperatures? Most likely we don't have that data, so we're going to say that this is going to be approximately equal to delta H at 298 under standard conditions minus T delta S under standard conditions at 298. And then that's okay because now we can calculate it, right? But you're going, well, we want non-standard conditions. Why are we using standard conditions here? If we're after non-standard conditions, how come we're using standard conditions?
Is it because we don't have the values of the unit, so we have to possibly?
Well, yeah, if we had the values, you're right. If we had the values, because delta G under non-standard conditions is equal to delta H under non-standard conditions minus T delta S under non-standard conditions. So if we have the values of delta H and delta S, then no problem. But the problem is we don't have these. Because can we say that delta H under standard conditions is about equal to delta H under non-standard conditions? In other words,
Does delta H depend on temperature?
yes, not that much, no. How about delta S under? Can we just go with this assumption?
Yeah.
Unfortunately, no. It would be nice, but we aren't going to do that. In fact, we aren't going to solve this because we don't. The problem is we're missing this data. We could solve it. This equation's correct, but we're missing the data here. And so instead what we're going to do is we're going to get delta G under standard conditions and correct it for non-standard conditions. This changes. And so this is incorrect. This is correct. And so the problem is figuring out what delta H and delta S are under non-standard conditions. Well, we don't have to do that because we can get this in terms of delta H and delta S under standard conditions and then correct it by this factor. And so even though we're after non-standard conditions, we're going to use these values under standard conditions because we're going to do a correction to those for non-standard conditions. Does that make sense?
If delta H and delta S don't depend heavily on temperature, then why can't we use those values?
We are.
So why is that?
We need delta H at this other temperature. We don't have it, so we're going to use delta H at 298. And the same thing with delta S. We need the delta S at whatever temperature we are, but we're going to use the 298. So. All right, so let's look at an example calculation. In this example, we're going to calculate delta G and change it by altering some stuff. All right, the first column is the delta H of formations. The second column is the delta G's of formation. The third column is the absolute entropy. The fourth column is heat capacity. And so delta H of formation, delta G of formation, and absolute entropy, S. And so I want you to do this. We're going from H2O liquid to H2O gas. Okay, I want you to calculate delta G two ways. I want you to calculate delta G naught at 298 Kelvin using this equation. That is delta H naught at 298 Kelvin minus T delta S naught at 298 Kelvin. And I want you to calculate delta G at 298 Kelvin, which is going to equal the sum of, the delta G's of formation of the products minus the sum of the delta G's of formation of the reactants. And there's going to be some coefficient here, mu they call it or whatever. It depends on how many moles of each we have. Okay, so you have the data here, and so why don't you try this calculation out and then see. Both numbers should come out the same.